So it should have not been hard at all for this warm-up. All four of them.
Yeah, that's the one I really I know. You know what sucks about this is that you don't know what they got. No, I don't like everyone. Yeah, I feel like it's getting too deep during school. Like, I see but I was
I wasn't here on Tuesday. Can I have Tuesday's notes, please? Thank you.
Alright.
like, okay.
Quiet down, please.
Sorry.
So this warm-up should not have been hard because we played this card game the other day. I had the 5 cards, 2 of them were aces. And then we select 2 cards, one at a time. Event A, Nolan, is the first card is an ace. Event B, the second card is an ace. Probability the first card is an ace is 2 out of 5. We put the card back. Probability we draw an ace again, still 2 out of 5. If we did it without replacement, probability the first card's an ace, 2 out of 5. We keep the card out, so then the probability the second card is an ace is 1/4. So today we're going to talk about independence. We have our last 2 rules. Next week we have review, and then your test is on Thursday. So, first thing, when we draw 2 cards with replacement, so that means we put the card back. We say that events A and B are independent. Bless you. Independent means the occurrence of the first event has no effect on the chance that the other event happens. So in the warm-up, when we used replacement, put the card back, the probability of B happening given A. B was we drew a second ace, given the first card was an ace, was 2 out of 5 because we put the ace back. So we know that events A and B are independent because the probability of B happening given A happened is the same as the probability of B happening whether or not A happens. So A happening had no effect on whether B happened. You could also switch it up and do probability of A given B equals the probability of A. Notice that A came first in the conditional probability, and it is the one that doesn't change. Here it was B given A, it matched the probability of B. So last time I taught you guys the general multiplication rule for finding the probability of A and B. Anybody remember that rule?
Oh.
Caleb?
Probability of A happening, B happens. Yeah.
Uh-huh.
Divided by the probability of A happening, B
Times the probability of B happening. Or A and B probability of B happening given A times the probability of A. Well, now, if two events are independent, the probability of B happening given A happened really is just the probability of B. So our multiplication rule gets simplified. And it becomes, I can't fit it on that line. I don't know why I made that line. Probability of A and B is the probability of A times the probability of B. Now that's only when we have independent events. If they're not independent, then we need to use that general multiplication rule that I showed you guys last time. Questions? Sorry. Before we actually use that rule, we're going to practice determining if two events are independent or not. And that's where these statements come into play. To show two events are independent, we have to prove that those statements are true. Am I off the board? Independence. So we're going to look at 3 different situations, and we're going to either show the events are independent or not independent. Everybody okay if I move my paper up?
Yeah.
Thank you, Nolan. Alrighty. Sorry, I am going to stack the deck to make sure that this works. But in the situation, I'm going to say I shuffled, but I didn't. At least I'm being honest about it, okay? So, first example, shuffle a standard deck of cards. Remember, standard tells you we take the jokers out. We're going to turn over the top card. Then we're going to put it back in the deck, shuffle again, and turn over the top card. Our 2 events are A, the first card is a heart, and B, the second card is a heart. And we want to see if the 2 events are independent. So the way that we show if they're independent or not is we want to see if the probability of B happening given A happens is the same as just the probability of B happening whether or not A happens. So we're going to look at B happening given A first. I'm going to put a deck of cards in the way. Everybody okay with that? Did you say no? I thought you shook your head no. Like, no, you can't put a deck of cards there. All right, I shuffled. I turn over my top card. Hey, look, it's a heart. A has happened. Wow. I know, right? So A has happened. I'm going to put the card back. I shuffled. I turn the top card over. It's a heart. So what was the probability this card was a heart? 13 out of 52, or 1/4 if you want to simplify it. Everybody good with how we got that probability? All right. Now, probability B happens with out the given that A happened. So I shuffle my deck. I turn over the top card. Not a heart. A has not happened. I'm going to put it back. I shuffle. What's the probability I get a heart? 13 out of 52. I flipped over, I get my heart. So since the probability of B happening given A happened is the same as the probability of B happening without A happening, these two events are independent. Questions? No? All right, so we're going to shuffle a standard deck of cards again. This time we're going to turn over the top two cards, one at a time. I actually shuffled and I messed up my stacked deck. That was brilliant. Event A, first card is a heart. Event B, second card is a heart. Same thing, we want to show that the probability of B happening given A happened is the same as the probability of B. Bless you. Thank you. So this time we turn over the top two cards. Top card's a heart. A has happened. What's the probability that this next card is a heart? 12 out of 51. I took a heart out, so there's no longer 13 of them. There's only 12. And there's no longer 52 cards. There's only 51. And I flip it over, and hey, look, it's a heart, because I stacked the deck. Sorry. I have way too much fun with this. All right, this time, just the probability of B. So I flip over my top card, not a heart. What's the probability this is a heart? 13 out of 51. So is the probability of B happening given A happen the same as the probability of B? No. So this time events A and B are not independent. Now, my plan was to let you guys try 3 on your own, but yesterday with 5th period, they really struggled with it. That's 5th period though for you. But, so I think what throws it off is for some reason, I stole this table from the textbook. And for whatever reason, they decided to use A and B to label the genders. And those aren't the events that we're interested in. And so I think the extra A and B threw kids off. So I'm going to do it with you. So we have 28 students in Mr. Tabor's AP Statistics class. They completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. We're going to choose a student from the class at random. The events of interest are female and right-handedness. And then, like I said, for whatever reason in the textbook, they decided to make A mean female and B mean male. So here where it says gender A, this is female. So put the little symbol, and then B is male. I don't know why. And like I said, I think that's what threw kids off, because our rule is written with A and B, but we're not interested in female and male. We're interested in female and right-handedness. So I want to see if those two events are independent. So I can show, I'm going to use F for female and R for right-handed. So I can show that the probability of female given the student's right-handed is the same as the probability of female, or I could do the probability of right-handedness given female is the same as the probability of right-handedness. Doesn't matter which conditional probability I do, as long as whichever letter comes first is the one I'm doing by itself. So, let's see, I'm going to use orange. So we want to figure out the probability the student is a female given they're right-handed. So since we're told that the student's right-handed, we're going to use the total number of right-handed kids, which there are 24 of them. Out of those 24 students that are right-handed, how many of them are female? 18. So the probability of the student being a female, knowing that they're right-handed, is 18 out of 24. Then we're going to compare that to just the probability of being a female. How many females are in the class? 21. How many total students? 7? 28. That's told up here in the problem. So 18 out of 24, does that equal 21 out of 28? Yes. I was hoping somebody would say no. Sorry. Just happened to be you. So 18 and 24 are both divisible by 6, right? So we can simplify this to 3/4. And 21 and 28 are both divisible by 7, so we can simplify that to 3/4. So female and right-handedness are independent for this class. Now I'm going to show you that it would have worked if we did it the opposite way too. So probability the student is right-handed given they're a female. So there are 21 females. Of those 21 females, 18 of them are right-handed. And then the probability of right-handed, there's 24 right-handed students out of the 28 total students. 18 and 21 are both divisible by 3, so this simplifies to 6/7. And 24 and 28 are both divisible by 4, so that simplifies to 6/7 as well. So like I said, sometimes the order is defined for you. Here it tells us A is the first card, so it would have to be B given A. Other times it doesn't matter the order for the conditional probability, so that opens up 2 ways to show it. Yes, sir?
Are there any questions like this on the test?
Yeah.
How will we know when we're supposed to find that specifically, how the probability of
Because I'll ask you to prove to me that they're independent or not, instead of just asking for a probability. Although, like you'll see in the next problem, can I flip? I may ask you to find probabilities and then tell me what those 2 probabilities tell you about the events. So here we have a 2-way table again. We have high school graduate, not a high school graduate, homeowner, not a homeowner. The totals are filled in for you. So there were 500 people interviewed. What is the probability that a randomly chosen person is a high school graduate? 310 high school graduates out of 500 total people. So probability high school graduate, 310 out of 500. If we know the person owns their home, what's the probability they're a high school graduate? So we're told they own a home. So we want to find the probability they graduated from high school if we know they own their home. We're given a condition, so that's going to change our bottom number. How many people in this survey own a home? 340. And of those 340, how many are high school graduates? 221 of them. Now, I'm guessing those aren't the same, but it's a little harder on this one to tell, so you might want to change them to decimals. So 310 divided by 500 is 0.62. That makes sense. I could have done that one in my head. 340, 0.65. So, see how I had you find a singular probability, and then I had you find the probability of that same event given a condition? Then I could ask you, hey, now that you found those two probabilities, what do you know about those two events? So what do the answers from 1 and 2 tell us? That A and B are not independent, or more specifically, graduating from high school and owning your home are not independent events. So then question 4 says, if we know that a person is a high school graduate, what's the probability they own their home? So this time we know they're a high school graduate. What's the probability they own their home? So how many high school graduates do we have? 310. Of those 310, how many own their home? 221. And let's look at that decimal. 0.713. So why are the answers for 2 and 4 different? Yeah, it's actually 2 completely different probabilities. Here we were told they own their home, and here we were told that they were a high school graduate, which, like Caleb said, we have different totals for those 2 things separately, so we're not going to get the same answer. So now we're going to use the whole independent idea to come to our last probability rule. And we're going to go back to the Mountain Dew idea. Can I move my paper up a little? All right. So suppose that Mr. Wilcox is determined to win a prize from the Mountain Dew giveaway. Recall that the probability of winning for each bottle is 1 out of 6. We're going to assume each bottle is independent of the previous ones. Mr. Wilcox buys 5 bottles Mountain Dew. We want to find the probability that he wins on all 5 bottles. What's the probability the first bottle is a winner? 1 out of 6. Now, we're told they're independent. So what's the probability the second bottle is a winner? 1 out of 6. What about the third bottle? 1 out of 6. Fourth bottle? 1 out of 6. And the fifth? 1 out of 6. Now, do I add, subtract, multiply, or divide these? Why? Because that's how I find the probability of independent events. So when our events are independent, we can multiply all the probabilities together. So what's a simpler way to write that? To the 5th power. 1/6 to the 5th. And then we can get our decimal 1/6 to the 5th. Sorry, there we go. What does this mean again? We put a bunch of zeros. This tells you it's in scientific notation. So that means we're multiplying by 10 to the -4th. Since it's a negative, we're going to move our decimal 4 to the left. If it was a positive, which in this class we don't really get positive numbers after E, you would move it to the right. So I'm going to move my decimal 4 to the left. So I'm going to have 3 zeros in front of that 1. So we get 0.000129 because there's a 6 behind that 8, so I'm going to round it to 9. Questions? All right, now we're going to find the probability that he wins on at least one bottle. And this is the last rule. It's not a rule in your textbook, but the question of at least one happens so often that I felt like it needed its own rule. What does it mean when we say at least one? One or more. So he could win on 1 bottle, he could win on 2, he could win on 3, 4, or all 5. So what's the opposite of at least one win? None. And we're going to use that idea to help us figure out the probability of at least one. So if we can figure out the probability that none of the bottles are winners, that's the opposite, and we have a rule that tells us how to find the complement or the opposite. So the probability of at least one win uses the complement rule. So we're going to do 1 minus the probability of no winners. We know the probability that we win. So what's the probability we don't win? 5 out of 6. And we want to not win on all 5 bottles. So we're going to raise 5/6 to the 5th. Five, 6 to the 5th is about 0.402. And then when I subtract from 1, we would find that he is going to win on at least one, about 59.8% of the time. Questions? All right, this time we're going to look at baseball. So in baseball, a perfect game is when a pitcher does not, that should say allow, not all, allow. A perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers should throw a perfect inning, meaning an inning where no hitters reach base, about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What's the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? So that part is key. We're going to assume independence. And we want to find the probability of a perfect game. To throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What's the probability of a perfect inning? 40%. So if I have 9 innings in a row, assuming the innings are independent of each other, I can take the probability of a perfect inning and raise it to the 9th power to represent the 9 perfect innings. 0.4 to the 9th. There's that E with the negative again, so we're going to move our decimal 4 to the left. So we get 0.123262. Questions? No? All right. You guys are going to try the one down below. Yep. Alright. They're both excused. Okay. All here. No Seth. All here. All here. All here.
Okay.
I was so sad. I was like, I thought that was so I will be there all day. No, I was like, ooh, but I think let's
Damn, really? Like, yeah, like a couple hours later.
it was like, you know what's so funny? It's like we had like another meeting today.
Have a good weekend.
And like the little leadership, like they're all like, it's such a like, I'm like, this is not the collaboration that it's supposed to be. This is not. Yeah, like guys, we had like artwork together.
Bianca!
Yes.
You hurt her?
Bianca.
Okay, no. Because she volunteered, and I told you it's gonna hurt. And so she did. She said, "Oh, it really hurts." I said, "Okay, you can let go if you want." She did not let go. I said, "Okay, let go." She said, "It really hurts." I said, "Let go." And she said, "No," and I was like, "Okay." And now she has that.
There were like
It's not
four
my
other
fault.
people.
She volunteered and she went like, "She's massive."
What was it?
It's salt and ice
Like
cream.
just a regular piece of ice?
Yeah. The salt makes it like
Chemical reaction.
it like makes the ice temperature really low, so it's like and your palm is really sensitive. Like this.
Was it like regular salt or was it rock salt?
It was regular salt.
Did it burn you?
Do you not remember the early 2000s at all?
Yeah, literally. I was like, you gonna put this or like no? I'm like, oh.
Yeah, you can buy like the what is it, the ice cream.
How do you remember the early 2000s?
I come from a different time period, swear.
Damn.
Fact, once the eraser burns, the salt, the
That was
stupid
not
thing, the big
the
time burn.
2000.
That was earlier 2000.
That was like the 2010s.
Yeah.
I was in high school in the 2000s, and we were not.
I told her to go. She said no. So.
You didn't do that. Those things I thought.
Listen, I told you.
Millennials.
No.
Nobody was actually using the
Oh.
You were in high school. Some people actually did have to go
Right, but those people had Darwin.
I graduated high school in 2005.
And it's bored.
Did you go to?
Yeah.
I did it wrong.
Thank you for trying.
I know.
My mom was sweaty around that time.
What'd you get?
I don't know, big guns.
Imagine you started like 0 to 931.
Oh, I didn't know.
Sorry.
Put money on Argentina or Neds.
What?
Argentina or Neds?
No, it's not making
Neds.
look
Why you think? I don't know. Why you like Fernandez or something?
You know why?
You think Fernandez is hot, huh?
Why?
Yeah.
But also, you have
Fernandez.
Yeah.
Have you seen that guy's arm? Bianca,
What?
have you seen that guy's arm?
What about it?
Dude, his tattoo's so bad.
My dad's
No, I'm just saying, bro. He's like really tight. It looks weird.
My mom just turned 23. Yeah, my stepdad's younger.
I stopped. I turned 21.
I also like.
You're definitely dead.
Damn.
Tiger. All right, Nolan is gonna help you guys out on this one.
Yeah, just like tell me what you want.
Me too.
He's lying.
Yeah, he's very sarcastic.
Quiet down. You guys should be writing down what Nolan is putting down.
When you get your Christmas wishes that we wish for you.
Yeah.
So it's not even like when you first
I know, they better do ours.
They better do it.
All right.
It's not, I don't want a lot for Christmas. There's just one thing I need.
guys aren't saying
Jar
this
pizza.
little.
Yeah, that's
All right.
She's like, well, my husband is in the room next door.
All right. So, this is one of those at least one things. So we want to figure out the probability at least one woman receives a positive. So it's easier to figure out the probability that no women receive a positive. Positive results happen 5% of the time, which means a negative result happens 95% of the time. I'm going to put this question on the test. Nobody's listening.
I'll get it right then.
Yeah, you will.
I'm here, I'm president.
I'm trying to write.
I'm trying to explain. So, if Lindsay, DJ, I know you guys got this already, but I need them to hear it too.
You know what really sucks?
Not just you
Is
guys.
that while I'm trying to read that to write it down, I write exactly how it's written, like the handwriting and everything.
So you're supposed to be
So
pretty good.
like my paper looks.
Pretty good.
No, that's
Like,
bad
oh,
handwriting.
Good for a guy,
Yeah.
no?
It's
Is that
good for a
Nolan?
guy.
Did Nolan write that?
Yeah.
That's what it is.
Oh, that's so funny because I was totally gonna guess you.
All right.
But then Sam was sitting over there, so I was like,
No,
oh, I don't want to hate on
Jenica.
Sam. So I was like,
No positives. Sam, 95% of the time we get a negative. So we want 100 women to get a negative result. So we raise it to the 100th power, and then we subtract from 1. So the probability that at least one woman is going to get a positive result out of 100 is 0.99408. There will be at least one questions on the test. At least once. Thank you, Emma.
You know I'm gonna ask, right?
It's on.
Yeah, okay.
I know. So before we look at the last little thing, let's add those 2 rules to our rule sheet. I hate saying the word rule. It just sounds weird. Rule.
Rule? Or maybe you just can't say it right.
Probably.
My mom, she can't say the word wall. She says wool.
I can't say
Second?
Everybody says
Yeah,
they say it
it's
here.
something.
Because I was like, I used to not know. I used to like bring it up a lot in elementary school. There was one that I was like, where is it?
All right. Let's see. What color have I not used? Orange. Okay.
I'm confused.
Wait, ask
What?
her right there.
What?
Okay, so Armenia, I
aren't
thought,
Armenians just Armenian?
I know, but
But like, are they?
since they're, okay.
But
I
is this
know,
like?
I know
whole
people
Russia
who are in
thing?
Europe, they're like European.
Okay, so
Or like
is,
American.
are Russians European or Asians?
Or Russian?
They're Russians.
Okay, but listen, so Armenia is in the continent Asia.
So is Russia.
Cool.
No, Russia's in both continents. So are they Asians or Europeans?
They're Russians.
They're Russians.
Okay, but
Bam.
So Armenians are
even
Armenians.
though they're still white, they're white AF. But like,
Yeah, they're pale. They're like pale, huh?
are they still considered like Asian though? Or
Russian? No, no.
They're considered Armenian.
I know.
I
not even
agree
close
with
to
that
Asian.
because the more populated area of Russia is in Europe.
They,
I don't
they're
know.
definitely just
I
Russian.
don't know.
Don't call them Asian.
I would call them Armenians.
I know, but then how does that make sense? People are like, oh, I'm European.
What?
I don't know. Ask
Like, are from like Italy or something, or like
Yeah.
Portugal? Not Portugal, Poland. They're like, oh, I'm European.
No,
Because their country is
They
in
say
Europe.
they're Eastern
Yeah.
Europe.
I thought they just say it all.
I know, but they still say they're European. So would like Armenians say like, oh, I'm like Western Asian?
It just depends where they live in Russia.
Okay, I don't want to hear you right now. Poland, I don't want to hear from you.
Oh, yeah, that's it. Yeah, they do say that too. I forgot about that one. All right. Multiplication rule for independent events, ladies. Jenica. We can find the probability of A and B by multiplying the probability of A times the probability of B, as long as they're independent. If they're not independent, you should use the one up above. So the key word that you're looking for on this one is independent, or assuming independence. I've used pink, blue, green, purple, orange, and maroon. I don't have any other colors. Let's go with black. Alright, and then my rule, like I said, that's not in your textbook, but these type of questions show up enough that I think we should make it our own rule. At least one. So the probability of at least one is 1 minus the probability. Oops, I forgot 1. That was silly. At least 1 is equal to 1 minus the probability of none. And then keyword there, at least 1. It's kind of obvious, but at least 1.
Do we get to use these rules of probability on the test? Like the sheet?
I haven't decided.
Oh yeah,
Yeah.
this is that's what you were talking about.
Yes.
Also, when I look through all the videos, does it show the rules in them too? So that I can catch up on all of them? Or
Yes and no. So I didn't update our rule sheet until
Last time.
Yeah. So here, I'm recording right now. So here's all the rules in a recording. Rule.
Hi, whoever's watching this.
Rule.
How are you?
Rule.
Are you in your house right now?
You tell me they listen to all of our
They
conversations.
just heard our whole
Yeah.
Someone could just like.
Oh, they did. Whoever's watching this are Armenians, Asians, or Europeans, or the Middle East.
they are Middle
Because
East.
it says it's a
They're Russians.
Great. Just like Russia.
Oh my God! What is
Yeah,
your
Russia's
obsession with
Russia.
Russians?
Do you think the
What's
Middle
your
East likes
obsession
Russia?
with Armenians?
Why do you
I was
love
just
Russia?
thinking
She
about
just would love
She
Russia.
loves-
All right.
Yeah.
They help us learn the animals.
Wait, I don't know if we heard this.
Oh, really?
Yeah. I'm like, I'm not gonna go out and buy freaking stockings on my feet.
I actually think I might have to
All right. Mutually exclusive versus.
I think I have
Miss Will, call Miss Will. Go bathroom today.
Why? That's okay. They won't get to leave early.
They're crazy today.
Dude, I'm gonna be so intense with
I
like.
can be patient.
Yeah, so we have to wear red.
Who do you want to win, Neds? I want Neds.
Stack as much stuff.
Unless, if the final's going to be Portugal and Argentina, that'd be pretty cool.
You could probably just
That'd be so
Santa
cool.
hat.
Wednesday, that'd be sick.
I wrote that down in like yeah. Yeah. Yeah, because this is our last week before break.
All right.
Which don't forget, we gotta do good on that.
I use ME as my abbreviation for mutually exclusive.
You can take it.
Jenica, what does it mean to be mutually exclusive?
That you're not dating anybody else.
That you're not dating anybody else.
And that you're not seeing anybody else or talking to anybody else.
So there's no mingling, right, with anybody else.
If you're mutually exclusive, it means that both of you are like, okay, like, you aren't seeing anybody.
Right. So here's somebody in a mutually exclusive relationship. We'll call them A. And here's B for Bianca.
For
No, it was A. No, because these people, this one's in a mutually exclusive relationship, and this one's not their significant others. So there's no intermingling, no overlap, no touching.
No touching?
No touching.
Don't forget it, Bianca.
If two events are not mutually exclusive, then they have the overlap, right? So these people are not in the relationship together. This person's in a mutually exclusive relationship, so they don't touch.
So it's like
Don't touch. No touching.
No touchy.
No benefits.
Well, I just was fully convinced
All right.
it was kind of like love on the spectrum where they were just all white. But it's not what it's
There's no way.
Now,
You're scared.
kids tend to get mutually exclusive and independence mixed up. So we're going to look at some events and figure out mutually exclusive, independent, both, or neither. And I'm using cards again because I love cards.
Do you even know any games with cards?
Yes, I know lots of card games. All right. First situation, we're going to select one card from a standard deck. We have event A is red. Event B, the card is a club. So first thing, are A and B mutually exclusive? Yeah, because I can't ever have a red club, right? So we know they're mutually exclusive. Then we want to figure out if they're independent as well. So we want to look at, is the probability of B, given A happen, the same as the probability of B? So probability of B, let's start there. It's a little simpler. B means the card is a club, excuse me. What's the probability I pick a card and it's a club? How many clubs are there? 13. There are 52 cards total. Now, I'm only picking one card. So if I know the card is red, how many red cards are there? How many red cards are there? Should not be a fraction. 26, right? So the bottom is 26 because I know the card is red and there are 26 red cards. Of those red cards, how many of them are a club? 0. Did I get the same fraction? No. So A and B are mutually exclusive, but they're not independent.
So
Yes,
are they
ma'am.
are they talking?
I think I know. I think
I can't hear.
How do we determine they're mutually exclusive?
So mutually exclusive means they can't happen at the same time. So a red card cannot be a club, so they can't happen at the same time, so they're mutually exclusive. All right, next situation, same thing. We're gonna select one card. Event A, the card is red. Event B, the card is a 7. So, mutually exclusive or not? Can I have a red 7?
Yes.
Yes. So these are not mutually exclusive. And then we're going to look at the probability of B given A and compare it to just the probability of B to see if we have independent events. So the card is a 7. How many 7s are there?
4.
And how many cards total? 52. So the probability of B is 4 out of 52. Probability of B given A happens. So we know the card is red. So how many red cards are there in a deck? 26. So the bottom is 26. Out of those red cards, how many are 7s? 2. Is 2 out of 26 the same as 4 out of 52? Yes. So these two events are not mutually exclusive, but they are independent. Any questions so far? Yes, sir.
Say, if it's mutually exclusive, then it cannot be independent.
Are you just basing that off this one?
Yes.
Why don't we
Or
see what
can.
happens here? There's one that we can't have. But let's see what happens. All right, so same thing. We're going to pick one card. Event A is red. Event B, the card is a heart. So, are they mutually exclusive or not? They're not mutually exclusive because we can have a red heart. In fact, that's the only kind of heart we would get. And then we want to see if they're independent. So is the probability of B given A the same as the probability of B? So let's start with the simpler one, probability of B. So what's the probability that my card is a heart? 13 out of 52. A is given. So it's a red card. How many red cards are there? 26 red cards. Of those 26 red cards, how many are hearts? 13. Did I get the same? No. So these ones are not mutually exclusive and not independent. Which combination did I not cover? Mutually exclusive and independent. I've yet to find one. I can't, yeah. Unless I really set the numbers up perfectly, but then it's not really a true life example. But I can't think of a card event where they're mutually exclusive and independent. I suppose if I could create it so there were zeros, but I can't. I can't figure one out yet.
Baby blue, like one piece.
Sitting for editing.
It always gets me every year. Like, I got it. And I'm also good by who
What did you ask?
What the score?
Yeah, that's it.
It's 0-0.
So then why did you ask what I asked? And you knew what I asked.
Because you gave me a weird look when I said that. And so you threw me
No, I
off.
went.
If I stayed with the card is red, the card is MP is a face card, right? So A is red, B is face card.
Oh, yeah. I see Nolan save his stuff away, so I can put mine away.
Probability of B. There's 1, 2, 3 face cards.
I'm checked out.
12 out of 52. That'd be 6 out of 26. Right? So that's independent. But
There's
those
like 4
aren't
of us,
usually
it's like
exclusive.
and we were talking about something.
Trying to figure out the exclusive independent cards.
Because like, he goes, we all go there. I don't know, he was just talking about a bunch of stuff.